The hypothesis tests for multiple regressions are very similar to the hypothesis test for one variable regression. Now that we have more than one regressor in the model, you can conduct a separate hypothesis test to see whether each coefficient is statistically significant. The steps are the same as before. At the beginning, you have to formulate a hypothesis. In the null, you state that the true beta is equal to 0. In the alternative, you state that the true beta is not equal to 0. Then, assuming the estimated beta hat follows a normal distribution, then you estimate the t-statistics using the estimator minus the hypothesized value, which in this case is equal to 0, and then divided by the standard error of the estimator. If the t-statistics is greater than 1.96 for a two-tailed test, then you have enough evidence to reject a null. Otherwise, you don't have enough evidence to reject a null. You can draw a similar conclusion based on the p-value. P-value for a two-tailed test is given by 2 times phi, which is the tail probability corresponding to the t-stat. And in most cases, we use the p-value of 5%, corresponding to the t-stat of 1.96 for a two-tailed test. P-value of 5% tells us that there is only 5% chance that the true beta will fall into the two tails outside the critical values. In other words, the probability that the null hypothesis is true is only 5%. The detailed steps for doing a hypothesis test for beta j is specified on this slide. The steps are the same as before. If you want to use the p-value to draw the conclusion, then for a p-value smaller than 5%, we say that we have enough evidence to reject the null at a 5% level. Otherwise, if the p-value is greater than 5%, then we don't have enough evidence to reject the null at a 5% level. Again, you can also use the t-stats to draw inferences. If the absolute value of t is greater than 1.96, greater or equal to 1.96, then we have enough evidence to reject the null at a 5% level. Otherwise, we don't have enough evidence to reject the null at a 5% level. For a one-tailed test, the critical value for t is 1.64, corresponding to 5% p-value. Let's look at the California schools example again. Previously, we tried to explain the variation in test scores using STR and the percentage of English learners in the class. The t-stats for STR is 1.1 divided by 0.43, which is roughly 2.3. Since 2.3 is greater than 1.96, then we can reject the null that STR is hypothesized to be 0, concluding that STR is statistically significant at a 5% level. Similarly, we can conclude that the percentage of English learners in the class is statistically significant at a 1% level, because the t-stats, which is calculated using 0.65 divided by 0.03, is very big. However, if we add an additional variable, the expenditure per pupil into the regression, the estimate for STR is reduced significantly from 1.1 to 0.29. And the t-stats also become smaller. 0.29 divided by 0.48 is roughly 0.6, which is much smaller than 1.96. And therefore, we cannot reject the null, and hence we conclude that STR is not statistically significant from 0 in this regression. From this example, we see that the effect of STR on test scores is not stable with the inclusion of additional variables into the regression. In other words, we haven't established a causal effect of STR on the test scores yet. This slide summarizes what I just said. The conclusion is that the effect of STR on test scores when holding expenditure per pupil and the percentage of English learners constant is not statistically significant is not statistically different from 0. In addition to using the t-stats and p-value, you can also use the confidence interval to draw conclusions for each of the coefficients. Specifically, you can carve out a 95% confidence interval for each coefficient and see if the 95% confidence interval contains the hypothesized value, which is 0 in this case. If the 95% confidence interval includes the hypothesized value, then you fail to reject null. Otherwise, you can reject null at the 5% significance level. The statistical significance of a variable tells us how likely this variable can be used to predict the variation in y. But it's not the only thing we care about. In economics and finance, we also care about the economic significance of the coefficients. Specifically, we want to know what are the economic implications of this variable and whether the economic implications are big enough for us to truly care about it. For example, you want to know what is the effect of having a college degree on hourly wages. You regress the hourly wages on a college dummy. If a person received 16 years of college education or more, then the college dummy is true. Otherwise, it's not true. The estimated beta is 3.8 for the college dummy. This means that on average, a college grad earns $3.8 more per hour as compared to someone who has not graduated from a college. The coefficient is highly statistically significant at 1% level, as determined by the t-stats, which means that college is an important factor in explaining the variation in hourly wages. Okay, that said, how much I care about going to college also depends on what is the economic significance of this $3.8. In the 70s, the average hourly wage is only $5 or $6 per hour, and therefore earning $3.8 extra is a very significant increase in the hourly wage. In this case, the economic implication of earning $3.8 is definitely significant. There are other ways to gauge the size of the economic significance. You can benchmark this $3.8 per hour against the previous findings on the effect of college on wages in the literature to see if $3.8 is bigger or smaller than the previously found impact. You can also compute the opportunity cost of going to college. Assuming that you earn $3.8 extra per hour for the rest of your life by going to college, then you can compute what is the present value of this extra benefit and compare it to the cost of an alternative investment or the cost of going to obtain a college education to see if it's worth, if going to college is worth it. There are other ways to gauge the size of economic significance as well. You can also think about the size of effect by converting the beta, the estimated beta, the $3.8 into a standardized beta coefficient. Recall that the estimated beta is given by R, which is a correlation coefficient between X and Y, times the standard deviation of Y divided by the standard deviation of X. If you multiply the ratio of sigma X to sigma Y on both sides of this equation, then on the left-hand side, you computed the standardized beta coefficient. And on the right-hand side, you reduce the right-hand side to effectively the correlation coefficient R. This means that now you can use the standardized beta coefficient to gauge the effect of one standard deviation change in X on Y, because the standardized beta coefficient is essentially the same as the correlation coefficient between X and Y. You can also gauge the economic significance by doing a what-if analysis. What if Evergreen Elementary District had Hillsboro's class size? Then how would it impact on the test score? Now let's pause this video and do in-class exercises 2 and 3.